I hope you can see my screen. So let me start. So today we start on this chapter, expectations. So uh, let us start with this following consideration. Suppose that x is a discrete random variable that takes values x1 blah 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 xn for some n. So finitely many values. And suppose that f is a mass function. F is equal to f of x is the mass function of x. Okay. And what does that mean? That means that there's probability that x takes a value xi is just f of I, f of xi. Okay. And then what you do is you just look at, so you imagine some set of particles or points, whichever way. And so let us say x1, x2, xn, and this has mass f of x1, and this has mass f of x2, blah blah blah. So this has mass f of xn. Okay. Uh, then you see, uh, yeah. So you look at this sum, the sum fxi summation xi fxi is called the mean or expectation of the random variable x. So the simplest situation is when there are n points x1, x2, xn, and each fxi is equal to 1 by n. That is, each one of these sets are capital X equal to xi are equally likely to occur, and with probability 1 by n. And then what will be this sum in that case? In that case, so in the special case, so I do this in the special case. When x fxi equals 1 by n for all n, so for all I, okay, we get the expectation of x. So this is denoted, notation is denoted E of x. We are going to define E of x in a more general context, but at the moment, just understand this. We get the mean of x to be, well, it is actually the mean x1 average xn by n. Okay. So this sort of justifies and when you have slightly more general one, okay, so yeah, these fxi's are all greater than or equal to 0, and in fact, when you have these discrete, our convention is that f of xi are strictly positive for these values, and they add up to 1. And in that case, instead of exactly mean, what you are computing is the weighted average. Okay. And that weighted average is called the expectation of X. Mhm. So, but where does the word expectation comes from? Okay. Actually, that word expectation comes from the following example. So it comes from gambling basically. Okay. So suppose that, so example, let me do this. Suppose that um, yeah, you throw, you roll a die, okay, and suppose that depending on the outcome, you win or lose, you win or lose uh, some some money, okay, uh, some money as given below, okay. So what is this thing? So possible outcomes are outcome, and then so this you can think of as well, part of possible outcome 1, 2, 3, 4, 5, 6. And the amount that you win or lose, let us say X, uh, should I say X? I call it, yeah. So let's just call this, yeah, I want to say X. See, this is your random variable. X associates to 1 the amount you gain or lose. So let us say if you throw 1, you lose 5 rupees. So minus 5. And if you throw 2, say you gain 10 rupees. This way you get 2 rupees. This way you get maybe 15 rupees. And here you get 20 rupees. And here you lose maybe 30 rupees. Okay. And it is perfectly legitimate to ask, what do you expect if you play this game many times? Okay, or what is the average expectation, whatever you say. So if you play this game, and let's assume that the die is unbiased, okay, it's a fair die. So each one of these uh, have equal chance of appearing. So probability is 1 by 6 for each one of them. So you can say your expectation of X. That is, when the payoff is as given here, expectation of X is equal to, well, you lose. So you see, on an average, each one of these numbers are going to occur 1/6 of the time. So minus 1, minus 5 by 6, plus 10 by 6, plus 2 by 6, whatever it is, 15 by 6, plus 20 by 6, and minus 30 by 6. So you can add up, and so that is your expectation. Okay. So this is the meaning. Okay. So you can compute this. Let me do it. 35, 45, 47, 32. So your expectation is something like 2 rupees. Okay. Yeah. So this is the sort of origin of the usage of the word expectation. Word mean is also used equally. So let us now do this slightly more generally. Suppose that X is any discrete. Suppose X is any discrete random variable. Okay. Uh, then, so this is a definition. So a discrete random variable with mass function uh, f f of x f yeah f is equal to f sub x. Okay, so if you recall, formally f is from real numbers to 0, 1. Okay, the mass function cannot take values above 1. It's always non-negative and takes values between 0 and 1. So uh, then what is the expectation of this? So this is recall. What expectation of x is defined then? Expectation of x is defined as, so this is the definition, summation. Well, I can write here, it takes well only discrete values, so I may just write here. Okay, just let me write this x fx. What does this mean? The same thing as summation x probability of capital X is equal to small x. That's what fx means. Okay. So yeah. So here x ranges over all possible real numbers. But notice that only countably many values here are going to occur. Okay. And what are those countably many? So because x takes only discrete values, so this fx is 0 except for countably many values xi. Okay, so this is same thing as summation xi fxi fxi I is equal to whatever. So yeah, this is it. So where f is taking positive values only on these xi's. So fx equals 0, fx equals 0, unless x is one of the xi's or some I. Okay. So here again, you see that there is this. So you can think of this as saying, well, yeah, you can rewrite this also if you like, xi, probability of x equals xi. So this number, probability of x equals xi, is sort of already, the probability function is already given to you. So you just have to compute it. This xi is like your stake. Okay, you may gain or lose or whatever. That number is what you would like to have as xi. And if x is a random variable for which payoffs for that game or xi, then summation over I xi fxi, this one, whatever it is, this is your this is by definition the expectation. I must make one small condition here, provided, because this time this is possibly infinite and xi can take positive and negative values, provided the above series converges absolutely. Okay. So just because you have defined something doesn't have to exist. It may exist, it may not exist. So here, yeah, I suppose the definition is now clear what we want to do. Okay. So let me do some simple example, maybe just one example. Before I talk about terms, more theoretical ones. So let us take, so suppose that x is a Bernoulli distribution with parameter p. What does that mean? x takes thus so thus f of 1 is equal to p and f of x equals 0 if no, sorry, just 1 second. Mm, yeah, the f of 0 is q. So there's only, it's like flipping a coin. So success or failure, probability of success is P, probability of failure is Q, okay, and probability of, so f of x is equal to 0 for all other x, for all x not equal to 0 comma 1. So this is the definition of Bernoulli uh, distribution, or yeah, Bernoulli random variable, and this is a mass function of the Bernoulli, yeah, distribution, Bernoulli random variable. Then what is the expectation of x? This is equal to, it's very simple, right? So you write here, first step, always a formula, xi, fxi. Here there are only two terms, and so 0 times q f of 0 plus 1 times f of 1, which is p. So this is just p. Another way of doing the same example, well, so this is also sometimes useful. So suppose that uh, x is actually the, yeah, so is equal to, we write it like this, I suppose, 1a, a is an event. So in other words, this is x takes a value 1, is a characteristic function of a. Okay, then also it is Bernoulli. X is equal to Bernoulli. What is a parameter? Probability of a. Okay, and therefore expectation of.
Sir, could you just briefly say what the characteristic equation means?
Yeah. So you just yeah. So it is a function defined on omega. So this omega is equal to 1 if omega belongs to a and 0. Sorry, this is getting too cramped. I'll write it again. Indicator function,
Okay,
characteristic
sir. So
function,
it's
they are all
similar to the indicator function.
indicator, indicator function. Okay. Okay. So this is equal to, therefore expectation of x is equal to probability of a. Just here you see, if the parameter was p, yeah, so probability of a. Okay. Uh, yeah, so let me,
Sir,
yes.
so why do we need the series to converge absolutely in the definition of expectation?
Yeah, I mean, it could so happen that the series doesn't converge at all. It may not even diverge to plus infinity. Sometimes people say, well, expectation is plus infinity if the series diverges to plus infinity. So it may neither converge nor diverge. All kinds of examples can be given, because you see, you can manipulate the payoffs or the values xi. Maybe I give an example immediately since you asked. I think it's better to spend some time, go a little slow, do examples. So example, um, so suppose that the mass function, um, let me first give us some, yeah, this example. Suppose that x is a random variable, x takes values, 1, 2, 3, blah, blah, blah. And yeah, with mass function. Okay, so I'm going to say, hmm, doesn't matter. Let's just keep it as it is. I don't want to change it. Now that I have written this, mass function f of k, yeah, okay. I just need to say what is f of k. F of k is a by k square, where so we know that a is equal to 6 by pi, 6 by pi square. Okay, this 6 by pi square is required to make this a mass function. This is true for k is equal to 1, 2, 3. Of course, it's 0 otherwise, right? F of x is, yeah. Let us do this. Then, what is the expectation? Expectation of x, you just write the formula, summation x f x, and that's also equal to, now, only value for which fx is not equal to 0 or positive integers, so k going from 1 to infinity, k 6 by pi square times 1 by k square, and now that is divergent. So this is 6 by pi square times summation 1 by k, and you all know that the harmonic series is divergent, so this is plus infinity. And you can give another example where things can alternate. So I mean, oh, yeah. So suppose I say another example, if you like. This time, suppose x takes values, takes values, whichever way. So you just play with it. It's nothing. And you know what I'm going to write? No, f of k is still 6 by pi square times k square. And what happens to this expectation of k? Sorry, x. Compute this. So, okay, sorry. I want to change this just so that, yeah, I had something in mind. So, let us write here uh, minus 36, minus 20, minus 16, minus 4, and then 1, 9, uh, 25. So it is squares of odd numbers this side and negative of squares of even numbers this side. So this both sides it's extending to infinity. And now you do this. The expectation of this is summation whatever. So okay. So you write this. Why don't you compute it? It will turn out to be something interesting. You just do this. So this is something which neither converges nor diverges. Does not exist. Okay. So the thing is, you can manipulate. See, fxi, by the way, these fx, they always take values between 0 and 1, and they always add up to 1. But x is in your hands. Okay, so you can manipulate this and make this as bad as you want. You want it to diverge, you can make it diverge. You want it to converge, yes, it is possible. And you want it to oscillate, you can do anything. You can ensure that you want it to behave the way you want it. You can make it behave the way you want it to behave. All right, let's just move on. Okay, so this is an interesting theorem, extremely useful theorem, really very useful, but proof is quite elementary. Let me write that. Okay, this is for some reason the book calls it theorem of the unconscious statistician. Statistician. So suppose that x is a random variable, uh, discrete random variable. So we have defined it only for discrete random variable for now. Okay, and y is equal to g of x, some function. Okay, then expectation of y, which is expectation of g of x, is equal to summation gx f of probability of x equals x. Okay, or this is same thing as summation gx f of x, where f is the mass function of capital X. Okay.
Sir, so shouldn't it be summation gx into p of x equal to gx?
No, no, it is. This is correct. You see that is what you should not expect that. For example, g of x could be, well, g of capital X could be x square. So capital Y could be x square. Okay.
Oh, okay, yes.
So let's prove this. It's an interesting result, and it's going to be extremely useful. Let me proof of that. Uh, so you just write you so just set up notation. See, one way to do that is compute the mass function of y. That's a little cumbersome. We don't do it, but eventually you will see that the proof is rather trivial actually. So e of y is equal to summation y probability of capital Y equals y. Okay. Having written this, we want to understand what is actually in some sense I'm doing exactly that. So this is equal to what is this? Or rather, let us just write this set. What is this set y equals y? This means that set of all omega such that y of omega is equal to little y. And this means set of all omega such that g of x of omega is equal to y. Okay. And what does this mean? Sorry, I need to change the page, but we can continue. So this is equal to set of all omega. Uh, so g of this, you can think of it as follows. So this is set of all omega such that x omega is in g inverse of y. Correct? And this you can rewrite as union. Okay. So x omega equals x. This is a set anyway. And g of x is equal to y. And you see, this is a disjoint union as you vary your x. Okay. Therefore, probability of this, it's better to write it. Probability of E of, no, probability of y equals y. Is equal to summation probability of x is equal to x, g of x equals y. Okay. Now substitute that. Therefore, E of y is equal to summation. So this is summation over y times summation g of x is equal to y, and here p of x equals x. But you see here y varies over all possible real numbers, and then you are saying, well, add only over those real numbers x, so that g of x is equal to y, and then do this calculation. So you can just simply rewrite this in terms of, basically you are interchanging the summation. Then this becomes g of x times probability of x is equal to x. Next times the mass function at x. This is it. Okay. You see, it's like saying, yeah. So I suppose, see, you just think about it. This is immediate from this step to this step. Nothing to say here. This is the important point is you are allowing y to vary over all possible things. Okay. And now what you are going to do is you allow, of course, y to vary over all possible things, but first group it so that, well, y takes a value. See, so it is like you are just interchanging. Uh, Here x varies over all possible things. Here x such that g of x equal to y. That is what this summation is. But you have now reversed the order of the summation. And when you do that, because y is equal to g of x or g of x equal to y here, this becomes g of x. That's all. Think about it, and there is nothing more to say. And this is x. Okay. And so you can apply this, and this leads to some important invariants. I will do that first. Yeah. So this takes us to the definition of moments. The terminology moments comes from considerations in theoretical physics. Okay. So, so expectation will be like first moment. The kth moment, so mk, the kth moment of a random variable, discrete random variable. See, later on we'll do, of course, continuous random variable also. So discrete random variable. Random variable x is defined as, here also you have to say if it is absolutely convergent, blah, blah, blah. So just as expectation of x power k. So, okay, therefore m1 is equal to expectation of x, m2 is equal to special things, expectation of x square, and so on. And just because you define it doesn't have to exist. We have already seen that even mean may not exist. Mean or expectation may not exist. Okay. And in this context, there is also moment about the mean. Moments, you can define it about any point, about well, you can just say alpha. Let me not worry about the most general thing. about the mean. About the mean, also called central moments. Central moments moments is defined as. So you see some notation is required. I am not used to this notation sigma k. We usually denote it by mu k, but the book denotes it by sigma k. So, okay. So this is a kth defined as. So sigma k. What is this? This is expectation of you sort of replace x by m1, x minus m1, and then take its kth power and compute its expectation, that is this one. Okay. And sigma 2 has a very special name. Sigma 2 is called the variance. And this is denoted as sigma square, where sigma, the positive square root, of course, is called square root of variance. So denoted as var x, variance of x. Square root of variance of x. By the way, is it clear that, let me write it, and then it's called standard deviation. Standard deviation. You may have studied part of it, I don't know, in your 12th standard. Deviation. Why is it that it makes sense to write square root of this? Why is it that variance is greater than or equal to 0? You see, when k is even, when you write x power k, expectation of x power k, it's going to be summation over x power k, fxi. Fxi are all non-negative, okay? And k even, so xi power k is also even, positive. Therefore, you are adding some non-negative quantity, and that means that variance in particular, or in general, sigma 2k, when k is even, sigma k is greater than or equal to 0. Okay. We need, so you see, okay, so we will see in a few minutes that it is possible to write central moments, moment about the mean in terms of the usual moments. Okay, how to rewrite it and so on. It's quite possible, and we will see that in a few minutes. But maybe one or two examples first. Yeah. I think I already worked out the example of, before doing that example, I think I should like to do one theorem. I think that theorem is important. Yeah. Let us do this theorem. This theorem is quite significant, although it's again very easy. Let me first state the theorem. Expectation operation has the following properties. The first one, let me see which one is. Yeah. Yes. Okay. So some properties are listed here. E of x is greater than or equal to 0 if x is bigger than or equal to 0. So what does this mean? Mind you that x is a function from omega to real numbers. So x omega is always bigger than or equal to 0. That's what it means to say x bigger than or equal to 0. And number 2, Ex is linear. E of ax plus by is equal to a times E of x plus b times E of y, providing of course Ex, Ey exist. If Ex, Ey exist, then expectation of ax plus by also exists and it is equal to this. So I have written it rather briefly without making full sentences. So and then so if you take this one, yeah, so let me just write here 1. What is this 1? This 1 is 1 omega, which is equal to 1. Okay. So proof. So this is trivial, right? The third one is utterly trivial. So on the whole of omega, it is just 1. Okay. So it is like Bernoulli with the parameter equal to 1. Of course, the expectation is then 1. And what about this? When x only assumes non-negative values, summation xi fxi is of course greater than or equal to 0. This is one is also true. Only 2 requires some proof. So we'll prove 2. Okay. So let z is equal to ax plus by. Okay. Then we need to understand these sets. So let and let small z be a real number, so that you get this set. Then z is equal to small z. This set is the same thing as saying set of all omega such that a times x omega plus b times y omega is equal to z. Okay. So now put just write instead of saying put x omega is equal to x write this, and y omega is equal to little y. And then what do you get? You see, the thing is, you may fix z, and a is fixed, b is fixed, a is given already there in the statement. So, but you see, you have a whole straight line of solutions. Ax plus by is equal to z. Z is fixed anyway. If you want, I could have called it c, but I won't call it z. Z is not a variable, but a fixed number. So I have a whole straight line of this thing, solutions for x and y. And for each point x comma y, I get a set and I take the union of that, and that is my this set. Then, so I continue to write capital Z is equal to small z is the set union over ax comma y, where this ax plus by is this straight line z. Okay. And where, so the union is over all those x and y such that this happens, where what is ax comma y? This is the set of all omega such that capital X equal to X and small x equal to Y, right? So this comma means and Y is equal to Y. So which we shall write as, you know, AX intersected with BY, where AX is capital X equals X and BY is capital Y is equal to Y. So you have sort of broken down the various components into pieces that we understand, which involve only individual random variables, capital X and capital Y. Okay? How does it help? So now you go back and start computing and we will see. So what is expectation of Z? Expectation of Z is summation Z in reals, Z probability of Z is equal. That's a mass function, right? So now you see why it is convenient to write in this notation, although it's discrete and only countable values are going to be there. Just sum over all possible things, because this is going to be zero whenever Z is not one among those countable things which really do matter. It's a convenient notation. Anyway, so this is equal to Z, summation is over Z, and this one probability, yeah, I'm going to write here, yeah, this is sum over the pairs x comma y such that ax plus by is equal to z. And here probability of the set event axy occurring, okay, which we may write. Yeah, I'll just skip maybe one step, I don't know. Okay, let me write it axy. So write this summation z summation, now you write y, and then summation right here x such that ax plus by. So the understanding is that now you, so far as this summation is concerned, y is fixed, and I am summing over all those ax such that ax plus by equal to z. And here this summation already I have fixed z. So you see now this is p of yes, so ax y. And now what we are going to do is change the order of summation. Sorry, somewhere I had this z, okay, and this whole thing. Maybe I should have changed the order in the earlier step. Doesn't matter, let's just write like this. So you see, I'm going to rewrite this as, so first write this summation over y, summation over x, and then summation over z, okay, but z is ax plus y, ax plus by times p of axy, right, like this. You see, you are going to sum over, so you are fixing an arbitrary z and summing over x and y such that ax plus by equals z. So that same thing as saying just sum over arbitrary x and y so that z equal to ax plus by, and change the order of summation, that becomes this z then becomes ax plus by. So that's all it is. And now I can rewrite it summation over y, summation over x. So here I write ax p axy summation by probability of AXY. Okay. And now, well, so you again interchange X and Y. So this becomes summation over X, AX. See, no restriction on X and Y now. See, that's the main thing. That's because the only restriction was over Z, and you changed the order and got rid of the restriction. And now you see summation over Y, P of AXY. What is this? So now you put summation over this. What is this? This is just, you see, you go back to the definition. Okay. Uh, yeah, where is this AXY written? AXY was written here. Now you allow fix an X, allow Y to vary. Y varies arbitrarily. That just simply means that I have omega such that X omega is equal to X. Okay. So I left out the omega here, but it's understood. So equivalently, you can say that AX is just this is union over AXY. Yeah, where Y is arbitrary. But when Y is arbitrary, AX intersection BY, but union over Y, but BY exhausts omega, and therefore it's just this is the same thing as. So after having said, so just this term alone, let me write it. Of course, we have one more term. I'll come to that. But let me finish this X, AX. Here, this is just a probability of X equals X. So here, summation over Y, same thing. Here, the summation over X, here you don't need to change the order already. So BY, and then probability of Y equals Y. Then plus summation. So by probability of Y equals Y. Oh, sorry. Here, okay, I skipped one step, I suppose, because I already wrote that here. If you want me to, I can rewrite this. Anyway, it's clear what is. So this is A times A is a constant for the summation. So A times expectation of X plus B times expectation of Y. That's it. Done. Okay. Yeah. So therefore, we can briefly say expectation is linear. Linear in what space? In the vector space of all random variables. On the vector space of all random variables, discrete random variables. At the moment, yeah. For which, yeah, the expectations exist. So, assuming expectations exist. Or let me write for which expectations exist. Okay. And so that proves this. Why is it that this is significant? Of course, it will be used several times in various considerations, but why is it that this is an important thing? You see, it turns out you developed probability theory starting with the function, this P. Instead, you can sort of recapture your P in terms of E. Okay, so this is because of the following. So suppose that X is equal to very simple, but it has much significance. Then expectation of X is equal to probability of A. We already saw that, right? Okay. Now it turns out that one can start with a tuple. Start with a tuple. Let me say omega f and e is the expectation operator. Okay. So on okay. So yeah, this. If you recall, the definition of random variable did not involve probability. It's a mass function which involved it. Okay. Now, if you have a notion of this expectation operator, you can get back your probability simply by saying, well, I will associate the number, real number, expectation of x for the indicator function, this Bernoulli random variables. Okay. So once you have it for or Bernoulli, yeah. So once you have it for that, you get back your P of A. Okay. For any A, this is valid, no? Okay. So you can as well start with some operator which should satisfy these following conditions. What are the conditions stated by this theorem? This is called positivity, by the way. Positivity. And this is linearity. And this is well, normalization, you may call it, because you want the whole space to have probability equal to 1, no? So now this is probability measure or something like that. Anyway, so once you have an operator E in an appropriate space of random variables, which includes all those random variables which arise as indicator functions of events, then you can get back your probability function. Okay, so this is an important viewpoint. At the moment, it makes no difference. It is just a remark, but later on, perhaps we will use this. Okay. Now, let us try to express. Yeah, that's right. Yeah, let us try to express this sigma square. What is that? Variance in terms of moments. Okay. More generally, you can do it, but first let us do it for this. Okay. So first of all, what is sigma 1? Sigma 1 is equal to x minus m1 power 1, but I omit that. This is same thing as expectation of x by linearity. So this you can just m1, so 1 should be identified with the constant function 1. So m is a constant function. So or constant random variable, which is just m omega, 1 omega here. So by linearity, this one becomes m1 times expectation of 1 omega, if you like. This is the only time I'll write m omega. After all, I'll just simply write m1. Okay. So this is E of x minus m1. But m1 by definition is E of x. So this equals 0. Sigma 2. Let us do sigma 2. This is equal to expectation of x minus m1 whole square. And one can expand that. This is expectation of x square minus 2 m1. So I treat this as a number. If you want, you can also treat it as an indicator function. Either way, you just check that. This is same thing as x and then plus m1 square. Okay. So now again use linearity. This is expectation of x square minus 2m1 expectation of x plus m1 square. But expectation of x is m1 square. So I get e of x square minus m m1 square, which is same thing as e of x, the whole square. This is a standard formula. This is the way it is written. Like I just keep that. So variance. So I write that is variance of x is equal to expectation of x square minus expectation of x the whole square. Sometimes we even omit the bracket and simply write square here. Okay, you should understand it. The moment you understand that expectation is a number square makes perfect sense. Okay, and here the variable, this is first of all, x square is a random variable. So you see, x is a random variable, y is a random variable, xy is also a random variable. And in that sense, expectation of x square minus this. Okay. If you are given the definition this way, it is not at all clear that this is greater than or equal to 0. But it is, because it is actually expectation of something which is non-negative. And yeah, positivity property. Okay, so it's not just for sigma square, you can do this for sigma 3 also, sigma 3, sigma 4, in fact for any sigma k. So I'll not expand on this, but write sigma 3. Sigma 3 equal to, so in general sigma k, in general sigma k can be written as e of x power k, and then some constant, in fact, that involves only binomial coefficients, except I can't remember, but you can derive it. Okay, so as a1 expectation of x power k minus 1, blah blah blah, and then some ak minus 1 expectation of x. Okay, anyway, for some constants. And these numbers can be explicitly worked out. Try this, it's an interesting problem. I'm almost done for today. Just want to, yes, I wanted to work out one other thing. So let x be the x is equal to binomial variate with parameters n comma p. And you all know what is expectation of x, right? Then, okay. So this is something that you can directly work it out using some identities involving binomial coefficients. There's a different proof given in the book. Maybe I give a different proof. This is also an interesting application. So note x is equal to x1 plus x2 plus xn, where the xj are independent, identically distributed. Do you understand this independent, identically distributed? They just abbreviate it as IID. It's a very common notation. Distributed. Bernoulli variate. Bernoulli parameter P. Is this clear to you, or should I explain? Have I said this before? Have we encountered this sentence? No? I don't know if there is still somebody in the audience because I cannot see your faces. But anyway, uh, so this only means that, you know, so you just think of, for example, coin toss experiment, uh, and then x is the random variable that counts the number of heads, where probability of heads is equal to p, probability of tail is q, which is 1 minus p. So you have tossed the coin n times, and xi be the, or x, I have written xj here, xj be the random variable which only looks at the outcome of the jth toss. Okay, so it will be taking the value 1 if the jth toss gives you heads and 0 otherwise. So it's a Bernoulli distribution with the parameter p. Okay, and now of course the jth toss and the ith toss are independent if j is not equal to I. And of course the total number of heads is, well, you add up all these random variables, that is it. So for example, if you are given some n is equal to some 10, so it may be tth, I mean something, some string of t's and h's having length equal to 10. And then what is x of that? It will just simply compute the number of heads. And that's what, and that is exactly, so what is x1 on that string of heads and tails? It will only look at the first outcome and it will be blind to the rest of them. And likewise, x2 looks at only the second one, but that's exactly same thing as counting. No, so this is the, that's the reason why x is equal to x1 plus blah 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 xn, where each xj or each xj is Bernoulli with parameter p, and they are IID, identical, independent, identically distributed random variables. Okay, and now this is very simple because we have already computed, uh, well, linearity. So by linearity, proof by linearity, linearity, this is equal to expectation of all these guys, and that's equal to E of x1. This is very linearity, and each one of this is p because each one of them is Bernoulli with the same. So this is NP. There are other ways of doing this. There is another nice way given in the book, and you do that. Okay, that way. And now I will do one more example. Let x be Poisson. Okay, so yeah, so let me do this. X be a Poisson random variable with parameter lambda. So x is discrete and it takes value 0, 1, 2, 3, blah, blah, blah. And probability of x is equal to k is e power uh, minus lambda times lambda power k by k factorial. Okay. What is the expectation of? So k here takes value 0, 1, 2, 3. Okay. What is the expectation of x? This is equal to, just apply the definition, k times k equals 0 to infinity, k times p of x equals k always write the formula as the first step, because this way the formula is reinforced, and not just the formula, the distribution, everything is reinforced. K equals 0 to infinity k e power minus lambda, and then lambda power k by k factorial. But this becomes, because first term is 0, so I may as well write k equals 1 to infinity k. So e power minus lambda is a constant. Let us write that here. Okay. And then k lambda power k, whatever, lambda power k. But this k and lambda power k by k factorial, I can cancel one k. And I just simply write here k minus 1 factorial. K minus 1 factorial. Always not. So I'll just try to squeeze that in, minus lambda. Now you see you can pull out a lambda out of it, because here I have k minus 1. So I put a lambda here. Then I write instead of k minus 1, so I write k equals, you see this, look at the starting term here, begins with 1. So if you like, you can write L, but we all understand what is happening. Lambda power k by k factorial again. That's equal to lambda. E power minus lambda is already there, but this sums to e power minus lambda. So that's equal to lambda, and that's the answer. Maybe I stop here for today. And if you have any question, you can ask me, or I stop lecturing.
Sir, like I had a question regarding that characterization. Can I ask?
Yeah, sure.
Yeah, so we have to prove that a function that a function will satisfy those three properties if and only if it is a distribution function of a random variable. So we proved in class that if it is a distribution function of a random variable, then it will satisfy the three properties. So uh, if we have a function that satisfies the three properties, then we have to construct a probability space. Is that the question, sir?
Where did you, are you asking about something that I did in today's class?
No. Like the previous, sir, like we did distribution functions.
Distribution functions.
Yeah.
Okay. So for discrete random variable or what?
For
So
general.
okay, see, anyway, you are given a certain function which satisfies certain properties.
So should we
And
construct a Should we construct a probability space? Like some problem.
actually, no, you see, the thing is the probability sort of takes a back. You, hmm, uh, you
So
should
like,
you should say you got to construct the random variable, right? It's a random variable that you are
but
constructing. You are
but
not constructing the probability space.
if the
Probability space
space,
is already there. Okay.
sir, but if the probability space is like a discrete, I mean, if it only has a finite number of elements and the function is continuous, something like that, then we have problems. Like we cannot construct a random variable, right?
No, but if the distribution function, if the function given to you is continuous, uh, okay,
Yeah.
capital F, uh, automatically that would mean that x cannot be a discrete random variable.
But sir, but if
If
the
you do
given
you
problem,
remember what is a do you either you give me an example or you tell me which question then I will explain to you more clearly. If you see, let us draw pictures. Sometimes it's much easier to draw pictures
sir,
and then
like what I was thinking was that like if like if we take the sample space to be R and uh, the
sample
sigma
space is
field,
our
sigma field generated by open
interval.
interval A, closed interval B
Okay,
subset,
it
and
doesn't
then
matter. Okay,
we take the random variable to be the identity function.
identity function.
No,
Okay,
the random then the probability of open interval A, closed interval B to be f of B minus f of A, where f is the given function.
Okay.
So
Yeah.
like this is a probability. So we have constructed a
No.
random variable.
I see. Okay.
Closed interval, open interval, closed interval.
Yeah. Okay.
And
Okay.
then
It does
identity
look better.
function is f measurable. So is
Uh, hmm.
so is this okay, sir? Like, or is this how we should do it?
Oh, so you are taking X to be.
Identity function.
No, but you are defining probability,
Yeah, yeah,
no?
yeah, yeah. I'm defining
No, no,
probability.
you are so okay. So sorry, that's not what is meant here. See, you are already given a probability space. Don't try to define P. P is already given to you.
Okay, okay, sir. Okay. So we
Okay.
have to. Okay,
See, that's why I'm saying. See, when I'm giving you a function, okay, and it may or may not be a distribution function. If you believe that it's a distribution function, and if you want to show that it's a distribution function, give an example. Find a well, I mean, uh, there are several ways to do this, no? So you don't have to construct your P ever.
okay, sir. Yeah, I thought
It's a random variable which you must construct.
just the random variable.
Or,
Okay,
see, I don't know in which context this problem arose. If it is a discrete random variable, you construct the mass function. If it is, sorry, if it is, if your given function capital F, okay, so let me explain in terms of a figure, okay? I think maybe that
okay,
is
sir. Yeah.
better. Yeah. So it may be that, so I, unfortunately, this line doesn't look like real line. Anyway, so this is a origin. Let us say up to origin, it is the distribution graph of the distribution function coincides with this one, but not including the origin. And there somewhere, say, let us say it is half, and then it stays like this for some time, and then maybe it takes off, and then it sort of goes like this asymptotically, becomes like one, or maybe somewhere it becomes one also. So this could be a point where, let us say, two, and then it is one. So this is y equals one line. Okay, and now, so here is, you make your test, and then you understand that this is indeed satisfying the conditions for it to be a uh, probability function. Sorry, for it to be a distribution function. Okay. Now,
Okay, sir.
the corresponding x is not going to be uh, uh, either discrete or continuous, the way I have drawn the figure. Okay, but you can say so. You can take x to be. You can, yeah. So this is a slightly complicated one, but never mind. So f is hmm. So let us take uh, x to be omega. Hmm? Sorry, omega to be real numbers, just for sake of convenience. Uh, or you can, you don't need to do this. You see, mm, you can say that x takes. I construct an x for you. That's a game, right? X takes only non-negative values, negative values, and and x equals 0. So here you see I put half, corresponds to a set A, such that probability of A is equal to half. Okay, and then what do I do? So it is like x is equal to already sum of two random variables. One is indicator function. Okay, indicator function of A, one of A, plus another random variable y. And this random variable y takes values. Let us say this is half again, uh, stays like this, half. Okay, then at half, to somewhere here where it becomes tangential. From there, you can sort of give a continuous function. So you can write a density function type of thing, no? So you just, so let us say this is 3 by 4, no? So again at 3 by 4, I need to, so let us say this is 3 by 4. It's becoming a little complicated the way I have done it. So this is indicator function of A plus I need to have one more indicator function of B, where probability of B is equal to the difference is equal to 1 by 4. Okay. And X takes the value, uh, yeah, when it is 0, it is taking the, so here, yeah, X is 1 minus this, I suppose. 1 minus this. And here, this is with some weight, I suppose, because I want it to be 1 by 2. No, so I put 1 by 2 here. At 1 by 2, it takes a value half. Okay, so sorry, I plus 1. I sort of, it's a mess, but let me write it again. This is indicator function of A complement plus 1 by 2 times indicator function of B. If you do this random variable, and then what you do is you have another random variable which takes values which corresponds to actually a density function, more or less. Yeah. So that density function is 0 up till here, up till half it is 0, and then it assumes this range of values. So one could give this y alone, you need to fudge things so that it works out okay. It should take, so I have drawn a figure here which looks like this, but so you see, I need to give some description for y. So y again is not going to be, I suppose, continuous, but at at uh, at the value, at this value, from here onwards, okay, from here onwards, it is given by, so a function which when integrated gives you area under this curve. That is the function that I want to have. Okay, I think that is very much possible. In fact, I think maybe y can be, I can just take, I think y to be uh, y to be continuous, I suppose. Yeah, y continuous. Let's just put that to be continuous. What is the y? So I should say, what is y of t? Y of t is integral over some function f of x dx, and minus infinity to t, and t is here somewhere beyond this half. Okay, t is here. And what is this minus f of x doing? F of x is 0 if x is less than or equal to half, and then it is some function. Okay, so if you assume that this is a smooth function, you can just take it to be the derivative of this. So in other words, when you, it can have a discontinuity, no problem. It is starting from here. So the this graph that you see is the graph of this function, which is actually integral half to t, sorry, half to t, sorry, I am getting a little delayed, and then fx dx. This gives you this portion. This is going to be some function, and that function you may call this g of x. So this g of t, g of t is just this value from here onwards. Okay, g of t. The difference between f of t and g of t is that f of t consists of two things which are having point masses. So you have to be careful. But otherwise, it is just this. I don't know if it makes sense. Here also there is some minor problem. The way I have drawn, I think it is okay. This is perfectly okay. So just check this. This must be the thing for which I have drawn the graph. So this is how you are supposed to construct your x or your density function little f. Okay.
Okay, sir.
Yeah.
Sir, I did not completely understand, but I'll see the recording.
Okay. Okay.
Okay.
Bye.
Thank you, sir.
Hmm.
Thank you, sir.